You know that AI learned to talk like a human being just by learning language patterns from text. Researchers just proved something wild. Transformers can learn the laws of physics just by watching simulations. No equations, no physics hard coded, pure pattern recognition, discovering how our universe works. Today, you're going to learn an alternative approach that computers can use to make new discoveries in science. I'm Evan Goldstein. I'm a licensed professional engineer and a data scientist. I'm building AI Capitalist to talk to the leaders and the thinkers, like you, about navigating this brave new world of thinking machine. Right now, when scientists are exploring the world of physics, they spend months retraining specialized computer models to solve each physics problem. We used to do this in engineering school. It was like you would build a simulation, you would do finite element analysis where you would map every particle moving of fluid through a pipe just to predict how it would act, and you would apply the laws of physics to each particle of moving water, let's say. But that means that every experiment and every simulation has to be designed from scratch using the laws of physics that we know, and then it has to be validated. What if AI could just watch a few examples of the world running as it does and then figure out the physics by itself? That's what this team did. They trained a model on 1.8 terabytes of simulation data, more than all of Netflix shows combined, and then they gave it zero equations. They just gave it raw physics snapshots. And this AI didn't just learn fluid dynamics or shock waves, it predicted entirely new phenomena that it had never seen before, like supersonic flows slamming into obstacles, with 29 times better accuracy than traditional models. No retraining, no hand-holding, just pure context-based physics intuition. Now, this is the sort of physics that powers everything from jet engines to climate models, and it works. And the kicker is that it maintained physical consistency for 50 time steps, like a video game that never glitches even after 50 seconds of play. But it's not just a game, and this isn't just an upgrade. It's a complete rewrite of how we simulate reality. Let's dive into this paper. This is towards a physics foundation model. We're reinventing physics for AI. Figure 1 is showing how they set up this experiment. The researchers were tackling something that sounds impossible. How do you build a single AI model that can understand completely different physics systems without being told what the rules are in the first place? So they've fed the model a 4D stack of data, which is like a movie where each frame of the movie shows temperature and pressure and velocity fields in a space. Now, the model has a neural differentiator and a numerical integrator. So the numerical differentiator transforms that. It figures out how things are changing, and the numerical integrator then takes that rate of change and looks for patterns and tries to predict what's happening next. Instead of figuring out or memorizing specific physics equations that describe the underlying principles, the transformer is learning to be a universal derivative calculator for physical systems. It's like training someone to be fluent in the grammar of physics itself, rather than just memorizing individual sentences in different physics languages. But here's where things really get wild. Now, here's figure 2, and the bar chart is telling a story that was actually pretty surprising. The researchers compared their model, it's called G5T model, against two established methods: Fourier neural operators and unit architectures. So those are what's listed here. All the models were trained identically to predict the next frame of 4 input frames. So they're playing the movie. It's like, think of it like a flip book. So they're showing you picture 1, then picture 2, then picture 3, and then picture 4. You have to guess what is going to be on that picture based on the motion that you see developing from each of these pictures. So this is a performance comparison chart. It has both average and the median mean squared error, which is the lower bars. Lower bars means better performance. They did this because they wanted to avoid misleading performance from outliers. And they're finding that they were able to program about a 5 times reduction in the error rate. And even their smallest model that only had 10% of the data going in to program it outperformed the full-sized competitors, which are the standard physics models that I was talking about earlier. So this isn't just about being better. It's about being better in a fundamentally different way. It's like comparing a polyglot who can switch between languages mid-sentence versus someone who's only fluent in one language at a time. Figure 3 is where theory meets reality. This is a visual prediction grid showing actual physics simulations next to what each AI model predicted would happen next. The experiment setup covers 4 different physics systems: incompressible flow around obstacles, shear flow shock waves with Euler equations, and thermal convection. You don't need to remember all. But it's looking at fluids flowing and predicting how they're going to come out, and it's testing it with different standard testing models. So the fascinating part is that while all the models do okay with simple, smooth flows, when things start to get chaotic and turbulent, shock waves creating sharp edges or turbulent convection with swirling patterns, G5T maintains very crisp and accurate details, but the other models start to blur everything out. Now you can see that here, right? You see how things are starting to blur? The G5T is remaining crisp and clear, and the other models here, it's starting to lose resolution. There's starting to be probabilities of which ways things can go, and it's losing the ability to predict with certainty what's going on in any one spot. And as we saw before, the error rate is low too. It's like watching someone perfectly mimic a very complicated dance while everybody else can only approximate the general movements. So now we get to figure 4, and this is where it really started to perform. The researchers threw completely new physics at G5T, things that it had never seen during training. We're talking about like supersonic flow, turbulent layers, and boundary conditions that didn't exist in the training data. And the experiment here is the ultimate test. Can a model trained on one set of physics problems solve entirely different ones? It's like teaching someone chess and then asking them to play checkers. Related, but some pretty fundamentally different rules. Now this is another comparison grid where it's showing known versus unknown physics. Now with all these models, including models that we're already using to predict behavior in the real world, IT correctly formed a bow shockwave around an obstacle that was placed in its way. What that means is that it's able to predict things that occur in real life that the other models were unable to predict, even without having the full body of knowledge of physics, the predictive equations built into it. It's just looking at pictures and watching what's happening. It's like watching a student who learned basic math suddenly solve algebra problems. Not perfectly, but enough to show that they understood the underlying principles. And this brings us to the ultimate stress test. So these time steps are how many images forward is it going? Is it looking forward? With the error, these are the error graphs, the rate of error between what this model is predicting and what's actually happening. Now, what's interesting in this model is that it's showing pretty much linear growth, other than apparently this two-phase flow problem. But most models would experience an exponential blow-up, which kills most models. So it would typically start off here and just be like a rapid curve upward. But for most of these, the error stays relatively under control, which means it can predict further into the future accurately. Now, what this means is that we're looking at the first real steps toward a universal physics engine, an AI that doesn't just memorize specific equations, but actually learns the deeper patterns that govern how physical systems evolve. Not perfect yet, but it's a lot closer than I thought we'd get this quickly. I'd appreciate it if you push the like button. It really does help the channel grow. So the first thing that strikes me about this whole thing is this is going to affect our philosophy before anything else. Our whole materialist outlook is scientifically based on the scientific method. Propose a hypothesis, usually in the form of some equation, and then you test that hypothesis in the real world. What this is telling us is that there may be other ways of getting to an answer. So far, science has been the only way to accurately predict events in the real world we see around us in the physical world. Now, there are other forms of philosophy that give us meaning and depth and direction and character. But this sense of materialism has really pushed everything aside in Western culture. So it leads to a great deal of nihilism and philosophical drift. But now we seem to have a competing method with AI of coming up with predictive models that can look at the same set of data and more accurately get to a conclusion that will be what actually happens in the real world. This is pretty mind-blowing. It's similar to when the first videos in Sora came out, and it would show like a fluids, waves moving, people walking in ways that looked very natural. And we thought that was amazing because we were asking ourselves, did they program some physics model into the system and then use that? Did they have some fluid mechanics? No, they didn't. They just did something similar to what this is doing. So we're basically taking that technology, those ideas about just making videos, let's say, in AI, and then applying them to the real physics world and getting real answers. From an AI capitalist perspective, this does get into some iffy territory. Say I make an airplane and I develop a physics model of an airplane, and then I fly that airplane, and there's some issue with it someday. But if it's based on a standard accepted method of calculating airflows over the wing, motion, all the different details drag into an airplane flying, then if there's any liability to be had, we can look at that model, we can figure out where we went wrong, and we can assign blame, we can do the insurance claims, so we can keep the economy running. The whole system is based, or really our economic system is based on this scientific method and materialist philosophy. Now we have this crystal ball, but the crystal ball does a better job of predicting the answer than our best scientific idea. Where does that leave us? What happens if something goes wrong with the airplane? Something breaks? Who takes responsibility? I don't know. It's in the neural network. This is an issue with a lot of AI. Also, think of self-driving cars. There's a similar challenge. Who's liable if the car gets into an accident? Is it the person behind the wheel? Is it the AI system, whoever programmed the AI system? But what if they were making their best faith efforts and their models were more accurate than anything that came out of our sort of equation-based physics? Maybe something to think about. On the other hand, traditional physics simulation is now becoming a luxury tax for engineers, because companies spend months and millions of dollars retraining AI for each new problem. It's like forcing a chef to relearn the entire French culinary canon every time they switch from a steak to a souffle. It's not just inefficient, it's a capital allocation disaster where talent gets trapped in manual rework and grunt work. The real capitalist pain point is that engineering teams are literally building entire physics models from scratch after they've already secured contracts. And that's why this new AI isn't just a tool, it's a weapon against the status quo. It can smash the simulation software industry by letting the model learn physics itself from raw data. No equations needed. It's not just about savings, it's about who controls real-time physical insight. When your supplier's AI predicts a shockwave before your engineers can run a test, you're no longer the client, now you're the variable. This isn't really AI solving physics. It's AI replacing the need for physics as we know it. Engineers aren't getting better, they're becoming obsolete. The real prediction is that by 2026, 40% of engineering firms using traditional simulation are going to pivot to this data-first approach or die. But here's the catch that most analysts overlook. The real danger isn't job loss, it's that this AI's accuracy means no one can challenge its predictions. If your model says a bridge is going to collapse at 3:07 p.m. and it's 29 times more accurate than a human-designed simulation, who gets blamed when it's wrong? The engineer who signed off, or the AI? The hidden game is capital shifting to firms with no human gatekeepers, where AI's output is becoming gospel. Now you're thinking, wouldn't this make the AI even more powerful? Exactly. So what's your take? Is this the death of engineering as a profession? The birth of AI as a new physics arbiter? Or is this just the quiet end of human oversight in the race for efficiency? Pick your reality, leave a comment.